Good morning, everyone. I'm Jinglei. Today I'll present our work on memory-centric design of smartphone storage software. It's joint work with Mike, Thomas, and Yongwei. So let me first guess what you most dislike about smartphones. Just now, Marcelon already mentioned one about draining power, and I guess another one might be low responsiveness. So hopefully these pictures recall your painful memories. However, they are only one side of the story. Do you really know what your app is doing behind you? Here is the IO trees of Twitter, and each line is fsync call. You know, fsync is expensive because it requires dirty data to be written back to flash. So you can see here are many fsync calls, and much prior work has shown that such behavior largely impairs both energy efficiency and app responsiveness. So someone may ask, why not simply get rid of these calls? It sounds like the saying, I just need a programmer. Now the version is that I just need a better programmer to overcome this issue. Unfortunately, it's not the case. It's not a particular programmer's fault. This issue has its root in the fundamental design and assumptions about smartphone storage software. So let's review the traditional design of smartphone software, storage software. So apps write data to local flash, either through a file system or through a database, and then the database also writes data to its underlying file system. So file system is the hub. Let's zoom in a little. So when a write arrives, it's typically cached in the DRAM, and then there are two ways that it's written back to flash. One is by system-wide flash, typically 5 seconds on Android Linux, and the other way is by explicit fsync calls. And databases rely on fsync to maintain consistency. That's why just now we saw so many fsync calls. After all, the key property is that we regard data as reliability only when data has reached the flash media, right? So that's the key assumption. With this background, we can better understand the programmer's dilemma. On one hand, they only have old-fashioned storage to use. It's designed for desktops and servers. It's been around over 20 years, and it never takes into account energy efficiency and app responsiveness. On the other hand, okay, you can refuse to use flash storage. You can just malloc memory and put everything in DRAM. However, if every app does this, that will be a nightmare for the OS memory management. And also, it would be lost if you close your app and reboot your device. And you definitely don't want to download everything every time because the time transmission is more energy and time consuming. So we wonder if there's a solution that can take both benefits from the two worlds, one with compatible storage functionality and semantics, and one with DRAM level performance and efficiency. We think memory-centric design is the answer. First of all, it keeps to the traditional architecture and interfaces. So apps do not need modification to switch to our system. We only have new mechanisms and policy inside the file system. And the key difference is that we regard DRAM as a long-lived store instead of a cache. So whenever a write reaches DRAM, it's literally reliable in our concept, no matter it's from a regular write or it's from a fsync. Then the flash is regarded as a flash layer, as a backup layer. So we only need to checkpoint data to flash at times that are optimized for energy and responsiveness. So our solution is practical, particularly on smartphones, because smartphones have favorable unique properties and different assumptions than desktops and servers. Next, I'll introduce our main new insights and our system design. So, this is the demonstration of the memory-centric design. Okay, the first insight is about data reliability. There are 3 reasons that we argue in-memory store is reliable enough for most apps. The first one is a smartphone has battery-backed memory. In the world of desktops and servers where power outage is the threat, battery-backed memory is considered reliable. The second reason is the software is also quite reliable nowadays because it's relatively simple on smartphones. According to our online survey of over 100 server users, only 60% users can recall a OS crash within the past months. So the third reason is that most apps are robust because they are networked. We investigated top 62 apps from Google Play. The number 62 is because we targeted at top 50, but also covers every category of the apps. Here's a list of apps that are robust to local data loss, and we can see that 54 are robust. We can examine some particular examples. Pinterest privacy policy says that your profile, pins, comments, likes, and any other information you provided are saved on the server. So even you lose your local data, it's not a big deal. Skype is a little different policy, but if you log in within 30 days, your messages are still available and can be synchronized with your other devices. So it's also quite safe. So we argued that apps are not so vulnerable to local data loss. Okay, so just now we discussed about data loss. Another aspect of data reliability is consistency. Inconsistent state can cause errors and crashes, so we have to find a way to guarantee consistency even though we trade off durability. So we introduce transactions to the original OS page cache. Essentially, the steps are like this. The system will open a transaction for writes that target at a set of files, and those writes cannot overwrite the current consistent state of previous transactions. So we need to perform compare write, and after that, new coming writes can coalesce until we close the transaction. Okay, and one of these different apps have independent transactions, so we can perform app-specific optimization. Okay, so data reliability is not an issue. Then we should consider whether we have enough resources to support this solution. We can see that thanks to the hardware development, the DRAM capacity is very sufficient now. So do you remember this screen background? It's Windows XP, right? And when you have 2 gigabytes memory for Windows XP, the speed is like flying. And now most smartphones are equipped with 2 gigabytes memory. Also considering that you only have 1 or 2 active apps on a smartphone instead of so many on a desktop, we can safely state that smartphones have sufficient DRAM to spare some for an in-memory store. Here's a quick look of the main components that we introduce into the memory. By the way, we named our file system MobiFS. We reuse the OS page cache, and each page is referenced by an entry in the write log, where consecutive entries are made into transactions. For more details, you may refer to our paper. Besides these mechanisms, we also need policies to decide when to close the transaction and when to do checkpointing. So next I will introduce another 3 insights and our policy framework design. So insight 3, this insight tells us the goal of our policy design for energy saving. First, let's take a holistic view. We found that write energy is dominant. That is over 15 times the read energy. So we only need to focus on write energy. Then, if we write the same amount of energy, the number of writes is not so important. The difference may be within 1.5%. So these insights tell us that we should focus on reducing the size of data that we checkpoint to flash. So how to achieve this? We did some quantitative study. The x-axis is the staleness, that is the amount of data that has ever been written to DRAM but not checkpointed to flash. And the y-axis is the ratio of how much data can be coalesced. So we can see that different apps have different curves. Just now we already linked the data size with energy consumption. So this figure reflects the trade-off between staleness and energy efficiency. Okay. Next, we'll see how we can find the trade-off point. Just now, I already introduced the metric, the ratio, we call it E, and the E curve. And even though we assume in-memory store is reliable, users still don't want to lose data, right? So our principle is that we'll try best to reduce data staleness, unless there's good reason not to do so. As a result, we will find the peak on the curve, because beyond that point, the E curve will drop down with the staleness growing further. So the algorithm is using a detection window of consecutive writes. When a new write comes, we'll slide the window by 1 step and feed a new E ratio to an incremental version of a linear regression. If the gradient is below a threshold, we will suggest a checkpointing. Okay, till now we only consider energy efficiency, and definitely there's other objectives, and that one of them is app responsiveness. So precisely speaking, just now, the trade-off point location algorithm does not trigger checkpointing. It only suggests to close the checkpoint, making it ready to be checkpointed. When to actually do the checkpointing is decided by the responsiveness-oriented policy. So to understand this policy, we need to know another two insights. The first is that we have to have flexible timing, because otherwise the flash activity can conflict with user interaction. And we found that the right time is when the device is idle. For example, when you are reading the screen content, that's the best time. So we have this policy based on interval prediction. Interval is the time between the current user operation and the next one. So we have to fit the transactions into the interval. And our basic rationale is to predict according to history. Here are two strawman policies, and we improve over them by this observation that users usually switch between two modes. One is long interval operation, and one is short interval operation. For example, when you are read a Facebook news feed, you may skip several and then look into one. So here's the state machine. You can see the short interval and long interval states that correspond to the two modes. Okay. So quick info about our implementation is on Android 4.1, and we reuse the flash management components of ext4 or BTRFS. We test with these two systems. And our experiments based on traces, benchmarks, and real apps on a smartphone device. So some figures. First about energy. The first figure is about the reduction of flash data size. The red ideal line shows how much we can coalesce data if we do not do any checkpointing. And we can see that ext4 loses a good chance to coerce data. That means to save energy consumption. And our MobiFS approaches closely to the ideal line. Here are only two examples. And on average, with the 10 most popular apps, MobiFS can reduce the flash data size by 53% compared to ext4. Okay, this is based on traces. Now let's see some real run on real device. We picked 3 apps of different f-sync frequency. So they are representative. On average, whole device energy consumption is reduced by 35.8%. Next, we evaluate responsiveness. Again, we will first base our evaluation on traces and then on real app runs. So, here we I only show figures from real runs. And we can see that on average, the file system I/O throughput is improved by 18.8 times. And if we run on database, we run a benchmark on database, the transaction throughput is improved by 11.2 times. Okay, and this figure shows the time spent on a script to operate these apps, and the average user operation delay is reduced by 51.6%. Okay, a quick comparison with related work. Essentially, we decouple durability and consistency. This pattern has been seen in other domains, and we contribute application in the smartphone context, and we have adaptive trade-off. And another branch is energy optimization. Some work sacrifice performance for energy saving. We achieve both. Okay, conclusion is we propose a new design, new insights, and transparent to apps, and achieve good performance improvement. So thank you. Questions are welcome.
How does your MobiFS keep the consistency when your device is suddenly powered off, like pulling out the battery?
Okay. So because we maintain a write log, and every transaction is atomic, so the consistency guarantee is point of time. So you can imagine that if you suddenly powered off, that the device is powered off, it equals to the situation that the system loses data at a point of time in history. Mm-hmm. That's our consistency guarantee. Okay.
So, yeah, let me dive in here because my question directly follows on this. So, I think a lot of times when people build apps on smartphones and they're putting data into the cloud, they expect that after they've had certain acknowledgments of data from a host, that host state is up to a certain point. And I'm just curious if in any of your tracing you saw issues that were caused. Did you try this with apps and try to see what happens? What if I roll their disk state back like 50 seconds or something? Does this mean that now my Skype app is going to send paid SMS calls multiple times, or do these kinds of issues come up with real apps?
Yes, you may spend more. I'm not sure if I'm understanding your question well. So when you sync with a cloud service, but your local data is very outdated, right? In our experiment, the time gap is around 1 minute to our worst case. Yeah.
Okay. Well, I'll take it offline.
Okay.
Thanks.
All right.
Hi. So you mentioned the amount of data to write to flash determines energy consumption. So can you comment what do you think if we use techniques such as I/O deduplication or compression to reduce the actual write to flash? Like what kind of?
Okay. Yeah, that will be a trade-off between computation and I/O, right?
Yeah.
So according to our experiences, computation is also energy consuming.
Yeah.
Yes, so that's why we designed a very simple linear regression algorithms, and we do not choose like a objective, some math model that may incur a lot of computation. Yeah.
Thank you.
Thank you.
So I have a question.
Okay.
So is your does your thing apply to every app, or can you control it so that the ones that you know are amenable to this and will sync in the cloud can use it, and the ones that, like my password keeper, that would maybe throw it away if you didn't save it and anything crashed, would not?
Yes, we currently we just put apps in different partitions. So maybe in future we can expose easy to use option for developers or users to choose whether or not to use our mechanism. Yes, because there are apps like, they really do not want to lose data. Right. Thank you.